At night, the world pretends to sleep, but the universe doesn't. While our cities dim, while homes fall quiet, strange things continue their work in the dark. Particles whisper across impossible distances. Matter pulses with a rhythm that never stops. And deep beneath our feet, something ancient stirs. In the shadows of the cosmos and the silence of the deep, there are wonders that do not shout, they don't demand attention. They simply exist, quietly rewriting the rules of reality. Tonight, we follow the trail of 5 scientific oddities, phenomena so strange they could pass for folklore, yet so real they force science itself to bend. Connections that ignore distance, crystals that move forever, tunnels through spacetime, creatures that reverse death, and colossal shapes that sleep beneath the Earth's mantle. These mysteries don't live in legends, they live in the dark, steady, patient, and waiting to be understood. Tonight, step with me into the quiet wonder of the night, where reality becomes a little looser and the universe reveals its strangest truths. Welcome back to LilWeird, and welcome to night 6 of our 12-night journey into the mysterious, the wondrous, and the scientifically strange. I'm Jane, your guide through this midnight expedition, and tonight we're stepping into the quiet side of the impossible. For this episode, we're leaving behind the dramatic, the loud, and the obviously strange. Instead, we're exploring something subtler, the quiet wonders that unfold when the world grows still. These are phenomena rooted in science, not story, but they carry the same electricity as folklore. Phenomena so bizarre they could easily pass for cosmic myths if they weren't already verified, measured, or mathematically allowed by the very laws of physics and biology. So, as the night deepens and the noise drains away, let's wander into the gentle strangeness of the universe. This is Night 6, 5 Scientific Oddities of the Night. Let's begin. To begin, we're going smaller than small, into the quantum world, where the night behaves differently. Here, logic bends, intuition falters, and reality reveals one of its finest, strangest secrets. Let's start with a quiet wonder that even Einstein refused to believe. Quantum entanglement is one of the most mysterious phenomena ever discovered, a behavior so bizarre it caused Einstein, Podolsky, and Rosen to challenge the foundation of modern physics. At its core, entanglement is simple in description yet astonishing in implication. Two particles become linked so deeply that measuring one instantly determines the state of the other, no matter how far apart they are. Imagine you place one particle in your hand and send the other to the far side of the galaxy. The moment you measure yours, the distant one knows and its state locks into place. This connection is immediate, faster than light, faster than time itself seems allowed, a direct violation of what classical physics calls locality, the idea that objects can only be influenced by their immediate surroundings. Einstein called it spooky action at a distance. Not because the math was unclear, but because the universe was behaving in a way he believed it shouldn't. But physics has a way of stripping away our assumptions. Decades later, in a series of groundbreaking experiments called Bell tests, scientists proved something astonishing. The correlations between entangled particles do not obey classical rules. They violate a mathematical boundary known as Bell's inequality, confirming that entanglement is real, observable, and a part of the universe's fabric. Yet, despite how magical it sounds, entanglement is not a tool for faster-than-light messaging. The instant connection cannot carry a controllable signal, only a shared outcome born from pure quantum probability. The universe permits the weirdness, but preserves its deeper rules. Still, the implications remain staggering. Entanglement also raises several important questions that scientists still discuss today. Questions that influence how we think about reality itself. First, if two particles change instantly together, what does that mean for cause and effect? In everyday life, something has to happen first before something else happens. Entanglement doesn't follow that pattern. When one particle is measured, both particles show their results at the same time, even across huge distances. There is no clear cause and effect between the two. Instead, the two particles behave as a single system. This suggests that our normal rule about how events influence each other may not apply at the quantum scale. Second, are outcomes real before we measure them? This is called measurement problem. In quantum physics, a particle doesn't have a definite state until it is measured. Before that, it exists as a range of possibilities. Only when we interact with it does it settle into one specific outcome. This challenges the common belief that things always have fixed properties, whether we look at them or not. And third, if tiny particles behave in ways that don't match our intuition, what else might we be misunderstanding? Quantum behavior doesn't match the way objects behave in daily life. This may mean our everyday experience only shows us a simplified version of how the universe works. The deeper layers, like the quantum world, may follow rules that feel unusual because our brains didn't evolve to understand them naturally. These aren't abstract questions. They influence how scientists think about information, communication, and even the future of technologies like quantum computing. They also remind us that parts of reality remain unexplored or not yet fully understood. Now that we've looked at the strange behavior of particles, let's move to something just as unusual, a form of matter that behaves in a way scientists once thought was impossible: time crystals. Time crystals are one of the newest and strangest phases of matter ever discovered. They're not crystals that float in the air or glow in the dark. Instead, they're systems where the atoms or quantum particles repeat their state over time in a stable, predictable rhythm. What makes this remarkable is that they do this without using energy the way normal moving objects do. Things that move normally slow down. Pendulums stop, vibrations fade out. Time crystals don't behave that way. Let's break down what that means in real life, because scientists have already built them. One of the most important demonstrations happened inside Google's Sycamore quantum processor. Scientists took qubits, tiny quantum bits, and pulsed them with regular intervals of energy. But instead of copying that rhythm, the qubits responded at double the period. This is the key. The system wasn't following the external push, it was following its own internal timing. Even more important, the pattern didn't break down. It stayed stable, which is extremely rare in quantum systems. This experiment proved that time crystals can exist inside quantum computers, a major milestone. Another team created a time crystal using a chain of terbium ions suspended in an electromagnetic trap. They applied a repeating pattern or laser pulses, but again, the ions fell into a different rhythm, one that stayed consistent and didn't fade. This was the first experimental proof that time crystals weren't just theory, they were real, measurable, and repeatable. Next came a surprising version, magnons, which are tiny magnetic excitations inside certain materials. Scientists observed the magnons forming a stable, repeating pattern, another time crystal, but this time in a system connected to real engineering fields like spintronics and magnetic storage. Suddenly, time crystals weren't just for quantum labs, they were showing up in more accessible materials. Recently, physicists created a time crystal inside liquid crystals, materials similar to those found in smartphone screens. This version is especially interesting because it could be observed under a microscope. The repeating structures were visible. The setup didn't require extreme cold or high-end quantum equipment. This made time crystals feel less like exotic physics and more like a new kind of structured material that can exist under everyday conditions. So, what does this tell us about time crystals? Across all these experiments, one thing is consistent. Time crystals don't run forever on their own. They're not perpetual motion machines. They're systems that are gently driven with periodic energy, and they respond with their own unique repeating pattern, a rhythm the system creates internally. They're incredibly stable. Quantum systems usually fall apart easily. Time crystals don't. They hold their pattern, repeating cleanly over time. They may also shape future technology. Because of their stability, they could help build durable quantum memory, error resistant quantum computers, ultra precise timekeeping devices, new kinds of information storage. Time crystals expand what we thought matter could do. They show that nature can organize itself not just in physical space, but also in time, a discovery that once was considered impossible. Time crystals raise several important questions that scientists are still trying to understand. First, if a system can keep a repeating pattern without losing energy the usual way, what does that mean for our current definition of motion and stability? Are there forms of movement we simply haven't identified until now? Second, why do time crystals stay stable when most quantum systems fall apart quickly? What exactly protects their structure? Understanding this could help us build more reliable quantum technologies. Third, time crystals were once thought impossible. So, what other phases of matter might exist that we haven't discovered yet? Are there more non equilibrium states waiting to be found? Fourth, how far can this technology go? If time crystals work inside quantum computers and even liquid crystal materials, will they eventually become part of real world devices? And finally, if matter can organize itself in time, not just in space, does this mean our current understanding of time is incomplete? These questions aren't just theoretical. They shape how I think about the future of computing, measurement, and possibly even new forms of matter we haven't imagined yet. We've talked about matter that organizes itself in time. Now, let's move to something even more challenging, phenomena that push against the structure of space itself. Because if time crystals show us what's possible in the microscopic world, our next oddity asks a much bigger question. What happens when the geometry of space-time bends far beyond anything we experience in daily life? To explore that, we step into the realm of wormholes and the strange theoretical material required to make them real. How space time could bend, and why we can't do it yet. A wormhole is one of the most dramatic possibilities predicted by Einstein's theory of general relativity. The idea is simple, a tunnel that connects two distant points in spacetime, creating a shortcut through the universe. Mathematically, wormholes are allowed. Nothing in the geometry of general relativity forbids them. But the problem isn't the math. The problem is what's needed to keep a wormhole open. A stable, transversable wormhole requires negative energy density, sometimes called exotic matter. This isn't antimatter or any known substance. Exotic matter would behave in ways no normal material does. For example, if you push on negative mass matter, it would accelerate in opposite direction. If you try to pull it closer, it moves away. It would also create gravitational repulsion instead of attraction. This repulsive effect is crucial. Without it, the walls of a wormhole collapse instantly under normal gravity. The tunnel pinches shut faster than anything could travel through it. Right now, exotic matter doesn't exist in usable amounts, but there are tiny hints of similar behavior in quantum physics. One example is the Casimir effect, where two metal plates placed extremely close together create a small region of negative pressure energy between them. But this effect is microscopic and temporary. It's nowhere near powerful enough to stabilize a wormhole. Scientists also point out that if wormholes were stable, they might allow closed time-like curves, a technical term for paths that loop back through time. In short, wormholes could allow time travel, at least in theory. This leads to huge inconsistencies with causality, and it's one reason many physicists think nature prevents large scale exotic matter from forming in the first place. Still, studying wormholes has real scientific value. It forces researchers to look closely at the relationship between gravity and quantum mechanics, two pillars of physics that currently don't fit together smoothly. Even though we can build or observe wormholes today, they act as a testing ground. By exploring the conditions needed to create them, scientists gain insight into the limitations of space-time, energy, and fundamental physics. Right now, wormholes remain theoretical, but they are theoretically consistent, which is why they continue to be one of the most intriguing scientific oddities involving the structure of space itself. Let's go to the fourth oddity, the immortal jellyfish, the animal that can reverse its age. The immortal jellyfish is a tiny species found in oceans around the world. What makes it remarkable is its ability to reverse its life cycle, moving backward from an adult stage to a younger stage when it's injured, stressed, or starving. To understand how unusual this is, here's a quick overview of its normal life cycle. First, it starts as a fertilized egg. Then it becomes a larva. Then it settles onto a surface and becomes a polyp. It then grows into a full adult jellyfish called medusa. For almost all animals, this process only goes forward. Once you become an adult, you stay an adult until you die. The immortal jellyfish breaks this rule. If it faces something life-threatening, damage, harsh environmental changes, or lack of food, it does something no other animal has been documented doing at this scale. It turns itself back into a polyp. The adult body collapses, its cells revert to a simpler, younger form, and from the polyp stage, it can grow into an adult jellyfish again. This is not healing, it's not regeneration, it's a full biological reset. Scientists call this process transdifferentiation, where a mature cell transforms directly into another type of cell. For example, a muscle cell could become a nerve cell. In humans, this is extremely rare. In the immortal jellyfish, it's routine. Researchers studied this organism for several reasons. First is longevity research. Understanding transdifferentiation could give insights into how aging works at the cellular level. Second is cell plasticity. It shows that animal cells can, under the right conditions, reassign their identity. And third is resilience mechanisms. It demonstrates an evolutionary strategy where survival isn't about avoiding damage, it's about rebuilding from scratch. Despite the immortal label, these jellyfish can still die. They can be eaten, infected, or destroyed by environmental changes. But biologically, they don't have a fixed lifespan. If conditions remain safe, the cycle can, in theory, repeat indefinitely. This doesn't mean humans can copy this ability, but each discovery in this species helps scientists understand how flexible life can be and how much we still don't know about aging on a cellular level. For our final quiet wonder, we're leaving the ocean, the quantum world, and the night sky behind. This time, we look downward, far deeper than any human has ever traveled, because beneath our feet, nearly 3,000 kilometers below Earth's surface, lie two enormous structures hidden at the boundary between the mantle and the core. They're as large as continents, denser than the material around them, and we still don't know how exactly what they are. Let's talk about the mysterious giant blobs beneath Earth. Two massive unknown structures deep below the planet. In the deepest layers of the Earth, far beyond the crust and mantle, scientists have detected two enormous masses known as Large Low Shear Velocity Provinces, or LLSVPs. There are only two of them, one beneath Africa and one beneath the Pacific Ocean. Each blob is gigantic, hundreds of times taller than Mount Everest and as wide as entire continents. If you place one on Earth's surface, it would reach the height of the International Space Station. We know they exist because seismic waves, vibrations from earthquakes, slow down dramatically when passing through them. This tells scientists two things. First is the blobs are hotter than the surrounding mantle. And second is that they are also denser by at least 1 to 3%. But what they're made of, how they form, and whether they're solid or partially molten, those remain open questions. So, what are the leading theories about blobs? Let's explore them one by one. First is that it's an ancient planetary remnants. One hypothesis suggests that blobs are leftovers from Theia, a planet-sized body believed to have collided with Earth 4.5 billion years ago, the event that formed the moon. Fragments of Theia may have sunk into Earth's mantle and remained there ever since. Second theory is dense material from billions of years of sinking crust. Another idea is that as tectonic plates submerge into the mantle, some parts break off and accumulate in these deep regions, forming massive, dense piles over geological time. And last theory is heat anomalies driving volcanic hotspots. The blobs might help explain why hotspots like Hawaii and Iceland exist. They could act as reservoirs that feed rising plumes of magma, influencing volcanic activity on the surface. So, why do the blobs matter? These structures aren't just scientific curiosities. They could play key roles in mantle convection, the slow churning of Earth's interior, volcanic hotspot formation, tectonic plate movement, and Earth's long-term thermal evolution. And in some models, the edges of these blobs might be linked to mass extinction events due to their influence on supervolcano scale eruptions in the distant past. Despite their size, we have only known about them since seismic imaging technology became advanced enough to create 3D models of Earth's interior. Even now, our best images of the blobs are reconstructions, patterns inferred from how earthquake waves bend and slow deep underground. We cannot drill down to confirm what they are. We can only observe how they affect the energy that travels through the planet. The giant blobs beneath Africa and the Pacific remind us that the planet we live on still contains structures we cannot see, reach, or fully explain. They move slowly on the scale of millions of years. They influence geology above them, and they hold clues to Earth's earliest history. They are quiet, massive, and ancient, hidden reminders that the inner Earth is still one of the greatest scientific frontiers. These massive structures raise some important scientific questions we still cannot fully answer. First, what exactly are these blobs made of? Are they dense leftover materials from Earth's earliest formation, or something that formed later through billions of years of sinking crust? Second, if they are remnants of Theia, a long lost planetary body, what does that tell us about Earth's past and the formation of the moon? Third, how do these blobs influence volcanic hotspots at the surface? Are they directly responsible for places like Hawaii and Iceland, or are they part of a more complex system deep underground? Fourth, do the edges of these blobs play a role in extreme volcanic events or long term geological changes? If so, how do they affect Earth on a timescale of millions of years? Fifth, why are there only two of them, one under Africa and one under the Pacific? What makes these regions unique compared to the rest of the mantle? And finally, as technology improves, what new information will seismic imaging reveal? Are these structures stable, or do they slowly evolve and reshape over time? These questions show how much of our own planet remains unexplored, not on the surface but deep below, where the quietest and slowest processes shape the world above us. Tonight, we explored five scientific oddities that don't shout for attention. They don't erupt, explode, or break the sky open. Instead, they exist quietly in the background of reality, shaping the world in ways we rarely think about. We look at the quantum entanglement, which challenges our basic assumptions about cause, effect, and distance. We explored time crystals, a new phase of matter that repeats in time and expands what we thought materials could do. We examined wormholes and exotic matter, a mathematical possibility that pushes physics to its limits and tests our understanding of spacetime. We learned about the immortal jellyfish, a biological reset button that shows how flexible life can be. And finally, we turned to Earth itself, to the giant blobs hidden thousands of kilometers below us, reminding that even our own planet still has unfamiliar structures waiting to be understood. These aren't stories of spectacle. They're reminders that the universe is full of quiet processes, strange behaviors that don't announce themselves but are still unfolding all around us. Some challenge how we think, some challenge what we assume, and all of them show that discovery doesn't always come from the dramatic. Sometimes it comes from paying attention to the subtle details we've overlooked. If tonight's quiet wonder sparkled something in you and you want to explore any of these topics a little deeper, I've added links and extra resources in the show notes, including a short list of books if you want to keep going down the rabbit hole. You'll find everything there. Feel free to dive in, explore, and follow your own curiosity wherever it leads. And if you enjoyed this episode, don't forget to follow the show, leave a rating, or share it with someone who loves strange science as much as we do. It really helps the podcast grow. Thank you for listening. Until next time, stay curious, stay wondering.